Okay, so this is the second class of Introduction to Number Theory. And so this is the first real lecture where we're going to start going through the material in the book. Okay, so we're on chapter 1. The first thing we're really looking at is an algorithm. So an algorithm is a procedure to mechanically go through a couple of steps, and reach the solution. Eventually we want more than an algorithm, we want a good algorithm. We want an efficient algorithm. But the first step to any problem is, can you solve it? Then you work on, can you solve it better? All right? So here is a standard problem. Primality. So we talked in the last class about what does it mean for a number to be prime. It's got to be at least 2, and its only factors are 1 in itself. 1 is called a unit, all the other positive numbers are composites, and we're not yet working with negative numbers, rationals, reals, or anything like that. I will risk asking if people have seen the movie Zorro with Antonio Banderas.
Yep.
Okay, so you're Antonio Banderas, I've drawn a circle around you, your world is the positive integers at this moment. Until I say otherwise, there are no such things as reals or rationals. Alright? So we want to find if a number is prime. You might ask, who cares? Alright, let me give you a motivation as to why we care about primality, other than this will be on the exam. Alright, here's 2 crypto systems. So version 1, P and Q around 10 to the 200, and they're prime. I give you N, which is P times Q. And the password is P or Q. So if you can factor N, you get in. Okay? Version 2 is I choose X is around 10 to the 5,000. It's a random number. I give you nothing, and the password is X. Which do you think is going to be harder to do? Get a 200-digit password, or I even tell you that the password divides this number that I'm publicly going to give you, or get all 5,000 digits right? Which do you think is harder to crack? Method 1, method 2? 2, right? 5,000 is bigger than 200, right? Why is 1 easier? I'm sorry, why is 1 harder and why is 2 easier?
It's hard to factor.
Well, but so screw factoring, right? If I don't, let's say I don't want to factor this, I can just try all the 10 to the 200 numbers. That's better than trying 10 to the 5,000 numbers. So I have additional information at my disposal, I'll forget about it.
It takes longer to check if something's prime.
Forget about prime! Stop obsessing with prime! Why would this be harder? I mean, you want to say it's harder because it's got 5,000 digits I have to get right. Doesn't that seem harder than getting 200? Alright, maybe the problem is we're focusing on all this primality shit. I'll have to edit that out later. Okay? We can forget about the primality. We just have to get 200 numbers. We can forget about it. Why is this easier? How does the computer tell if you're right?
It doesn't have to check P or Q, it just says X is right, but it's not.
So how does the computer know if you gave it the right password? What does the computer have to do?
Check bit by bit.
Check bit by bit. So the computer knows X. Does the computer need to know P or Q? What does the computer need to be able to do?
Feedback.
It has to divide. Computer doesn't know P or Q. In fact, what they sometimes do is the computer that's used to generate the primes is destroyed. The advantage here is the computer knows the password. You can torture the computer. It's fun. The computer has to have the information written down in memory. You have the ability of somehow grabbing that information. This is the classic, I'll know it when I hear it. You can have a really dumb security system. And I'll know the password when I hear it, but if I don't hear the password, you're not in. I'm sorry, your answer doesn't matter. I don't know what the answer is, I just know that you're wrong. This is one of the great examples of why we care about prime numbers. 10 to the 200 is so big that for all practical purposes, we're fine. And we'll do a calculation in a moment or two to just see how big 10 to the 200 actually is. So this is hopefully some motivation as to why we care so much about prime numbers. So I want to figure out an algorithm for factoring n. So in the first class, I think someone suggested check all numbers up to n minus 1. So this is going to take on the order of n steps. If n is of size 10 to the 200, this is bad. I'm willing to assume right now that all the steps are equally expensive. That checking a 700-digit number of size 10 to the 100 is as expensive as checking a number of size 5. Just ballpark estimate, it's going to be order n steps. Then somebody had a great idea. Check up to n over 2. This is a 50% improvement. 50% improvement is not that bad. Your paths were down by 60, now only down by 8. 50% improvement. That's not enough. It's not enough. We need to do much better. Can anybody do better than n over 2?
Square root of n?
Square root. So check up to square root of n. Because if n equals x times y, if both numbers were greater than square root of n, their product would be greater than square root of n. So at least one of x or y has to be smaller or less than or equal to square root of n. Let's find the smaller factor. So we only have to go up to square root of n. So the question is this good enough? So let's say we're doing numbers of size, let's say 10 to the 300. All right, I'll bump it up a little bit. So let's say p is around 10 to the 300, and I want to check and see how long would this algorithm take. Right. How many seconds are there in an hour? I'm sorry, how many seconds in a minute?
60.
Okay, I really don't want to multiply with numbers like 60, so let's say there's 100 seconds in a minute. I'm going to make the numbers a little bit easier for me, and I'll round up a little bit. How many minutes in an hour? 100. Just because this is being recorded, I'll put not just scale. All right. How many hours in a day?
100.
Yeah, let's do 100. How many days in a year? 1,000. Yeah. I mean, we could almost fully round down with all the rounding up we've done. So 1,000 days in a year. So this gives us approximately 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the 9th seconds per year. Anybody know roughly how many thingamajiggies, doohickeys, thingamabob-majigs there are in the universe? How much stuff is there in the universe, roughly?
On the order of like 10 to the 81st?
Yeah, something like that if you're doing like particles, but then if you have like photons, I think you get like around 10 to the 89. Let's round up. Let's say 10 to the 100 objects in the universe. Okay? Let's say each one of them is a supercomputer devoted exclusively to our use. This is a somewhat unreasonable assumption. But I talked to one of my econ colleagues, and he's willing to make this assumption for me. They have no problem with stuff like this. So we will assume every object in the universe is a supercomputer devoted exclusively to our use, running continuously without error since the dawn of time. How many computations do you think a supercomputer should be able to do for us in a second? Roughly.
10,000?
10,000?
Let's say 10 to the 100.
Okay, 10 to the 100 is actually getting too ridiculous in terms of what we can do. We'd still be okay for this problem, sadly with 10 to the 100. 10 to the 10 is around, I think, the limit of what you can really expect a computer to do. I'll square it and I'll give 10 to the 20. This is way beyond our current technology. So say 10 to the 20 checks per second. So what this means is in 1 year, we have 10 to the 9 seconds, 10 to the 100 objects, 10 to the 20 checks per second. So in 1 year, how much do we do? I'm sorry? Was it 129?
Yeah.
Okay. The square root of 10 to the 300 is around 10 to the 150. So what this would mean is we would be short by about 10 to the 21 years. After just 1 second. Well, the universe has been around for probably on the order of 15 billion years, not even close. So if these computers had been running since the dawn of time to factor a number, we wouldn't even be close to the numbers that are being used in cryptography today. The reason to do this calculation is to give you some sense of why people might think stuff like this is secure. When we get to RSA and we get to encryption, we'll talk about World War II, and the Germans had a system called Enigma, which they believed was just unattackable with current technology. Now, the reason it was attackable was sevenfold. One is we had some very clever mathematicians. Two, we had spies who got us a lot of the information and working models. We also had computers, which we were able to use to automate a lot of the processes. But one of the big things was some carelessness on the Germans. And so they didn't do things as carefully as they could have, and they left really small gaps, which allowed us to narrow down the calculations. So there are certain types of numbers which are easy to factor. You stay away from numbers like that. Now, that's not what the Germans did, but I want this point here. Okay? So this gives you some sense of, we have an algorithm to factor, but for practical purposes, this algorithm is useless for the problems that are out there industrially. And this is why people think things like e-commerce should be secure. Okay. Any questions on this? So Wednesday is probably going to be a coding day. I want to do 1 day of class devoted to just talking you through how you attack a couple of problems. If there's a problem in particular you'd like to see, email me and I will try to work that into the lecture. I mentioned here that this is an algorithm. This first step is to have one. The second step is to do it quickly and efficiently. I will end with my favorite example. How many of you have done a Sudoku? Okay. Is there anybody here who has not done a Sudoku? All right, so everybody knows a Sudoku. Great. I recently did this in my son's 4th grade class, and there were a few people who didn't know what a Sudoku was, so I had to explain it. So I will do the more common ones where you break it up into 9 blocks, and in each row, in each column, in each block, you have to have numbers 1 through 9. If you want to check and make sure that somebody gives you a Sudoku, a claimed solution, is it easy or hard to check and see if they're right? It's easy. You don't really have to have that much knowledge to check and see if the Sudoku is right. Is it easy or hard to solve the Sudoku? Much harder. Okay? If anybody's interested, I've actually written a mathematical program to solve the Sudoku. There's a lot of good algorithms out there to attack them. Happy to talk about stuff like this. How many checks do you have to do in this row to make sure this row is good? So we have 9 checks per row. So how many row checks are there? So 81 row checks. And then similarly, it would be 9 checks per column. It would be 81 column checks. And then 9 checks per box for 81 box checks. So the total would be 234 checks. That's a lot of checks to write.
245.
Okay. Oh, sorry, I did it wrong. Transposed it. Even worse. All right. I'm going to show you how to cut down on the checks greatly. one of the big things you want to think about in mathematics is what do you want your variables to be? A lot of times, people use x for the unknown. Or if it's an integer, we use n. If it's a prime or probability, we use p. We try to choose notation that is easy to glance down and see what's going on. What can you tell me is probably true between little f and big F? What would you guess?
They have some relation to each other.
Yeah, any relation you might remember from previous classes?
What was the derivative? What was the antiderivative?
Yeah, which one do you think is the antiderivative or the integral? Yeah, big F is the antiderivative of little. And if you write it like this, you glance down and see what's going on. In my probability class last semester, there was one moment in time when nobody saw how to continue attacking something. I took two terms in a product and I flipped their order. Does it matter which way I multiply? As soon as I flipped it up, oh, we do the following. The way information is presented really matters. You want to take time and think, what's a good variable? When you do things in Sudoku, what variables do you use for the entries? What's the standard elements for Sudoku?
1 through 9.
1 through 9. Have you ever seen the all-vegetable Sudoku? You know, carrots, broccoli, cauliflower. No. God, that'd be horrible to use, right? How many of you have ever played the game 2048? How many of you ever played the NESCAC version? The NESCAC version, I know. What tile, what school do you think represents the 2048 tile? Williams. What school do you think represents the 2 tile? Amherst.
But what represents the 40, 48, no, 40, and 60?
I don't know. Maybe an honorary degree from Williams? Which do you think is easier or harder to play? 2048 with school names or 2048 with the numbers 2, 4, 8, 16? Which would you rather play? Numbers. I can quickly glance down and see, oh, 8 times 8 that combines, and see which way they go, and see which one they're going to go to. You know, I can still see, oh, okay, Connecticut College, that's one of the schools, right? Connecticut College and Connecticut College will combine. Oh God, what does Connecticut College combine to? But if you do it enough times, you start to remember and you start to learn. Does it really matter what label I use? No, but it can affect how quickly I can do things. Here's better labels. 1, 10, 100, 1,000, and so on and so on and so on. Now, it's a little bit harder to write these in the box. I'll leave that as an exercise for the reader. The advantage of having my labels 1, 10, 100, 1,000, etc. Each row has to have one and only one of these. What is the row going to sum to if it's correct? 111,111,111. So all sums are 111, 111, 111. If and only if. Have you seen 2 F's mean if and only if? If and only if correct. So now, rather than going through and saying, is there a 1 in this row? Is there a 2 in this row? Is there a 3 in this row? I just add once. Is it 111 million, 111,000, 111? Yes, great, I've checked everything. 1 check. 1 check for each column. 1 check for each box. How many checks? 27 checks. So the question is, how much of a savings is this? What you really want to do is you want to look at an n squared by n squared Sudoku and see how the number of checks is being saved in that. Here it looks like I'm saving 10%. I'm sorry, I'm saving a factor of 10. And only have to do 10%, which is pretty good. Maybe it's even better if I look at a larger board, I'm going to maybe save an enormous amount. So again, one of the fortunate things about this class is there's really not a fixed set of material we need to cover. The small amounts that I have to cover just so I can hang my head up high and say, yes, I taught number theory at Williams, is really small. We have a lot of freedom in terms of what we do. I really want to use the time to talk about the problems, the thought processes, how you would formulate things. Most of you are not going to be professional number theorists. That's fine. You know, I happen to be a professional number theorist. I think it's a great life. But What I want you to get out of this class is the thought process, how you attack something. That's going to be far more important. Spending a little bit of time thinking about something like this. What labels do I want to use? It matters. I've seen great studies about people who play bridge, and if you change the suits from spades, hearts, diamonds, clubs to 4 vegetables, the bridge experts, okay, fine. Spades is now cauliflower. I can deal with this. But the people who aren't expert are now thrown because it's not what they're used to. Really think about your labels. Think about what you're doing and think about choices and savings. Now for a computer, is it hard for a computer to do 243 checks? No. So it's really not necessarily worth doing it for this problem, but this illustrates a general principle. That if you spend some time, you can make an enormous savings in what you need to do. And what you could do now is look at a Sudoku. Now this was a 9 by 9, so this was a 3 squared by 3 squared. So maybe we could generalize to an n squared and an n squared in each of these blocks. And if you do something like that, look at how many checks you would have as n grows. So that's a really good exercise if you want to make that an extra credit problem. And email me how much would you save if you tried to do the checks like that. Okay. Any other questions on this? Okay. So we've talked about how you would factor numbers. We've talked that, unfortunately, the brute force algorithm is painful and it's not going to be practically useful. Now the other thing is I'm erasing this right now because this is horrible. There is not 100 seconds per minute. There is not 100 minutes per hour. So can somebody give me the correct values? 60. The next correct value? 60. Why the hell are we doing things like 60? Whose fault is this? Who did this to us?
British.
No. This is not the British.
Was
Yes.
there an ancient civilization that used like base 60 to do everything?
Yes, and it did. And now, I'm not saying that they died out because they used base 60, but
I don't remember who it was, but
the Babylonians, they're gone. They used base 60. Now, the Romans used Roman numerals, stuff like this, just to choose 2 random Roman symbols.
Egyptian was base 16, right?
Egypt was base what?
16?
16.
Yeah, which is horrible, more than 16.
Well, it depends. There's advantages of base 60. So we mostly do things base 10 in the decimal system. And there will be times when we'll be looking at properties of numbers and we'll be looking at properties of digits. And one question you can ask is, does it change if we work in a different base? Why do you think we work in base 10? 10 fingers, yes, right? We have 10 fingers. Do you think the universe cares that we have 10 fingers?
For sure.
For sure. Now, this is unfortunately outside my pay grade. It is outside the realm of what I'm allowed to cover in this class. I am not allowed to discuss whether or not the universe cares or does not care if we use base 10. I have some personal views on that. I'm happy to talk about it over a cup of coffee or something stronger. But I will say is we use base 10. Why would the Babylonians use base 60? Did they hate their kids? Did somebody do this to them and they wanted to get... Well, who started this?
It's easy to manipulate 60 because it's divisible by a lot of numbers.
Excellent. It's easy to break 60 up. What goes into 60?
4, 3,
I'm
1,
sorry?
2,
1, 2, 3,
4,
4,
5,
5.
6.
Okay, so by induction, every number seems to go into 60. All right, finally find a number that does... Okay, so 7 doesn't go in. Does 8? No. 9. 10. Yeah, 10 goes in. 11 doesn't. 12. One of the interesting questions you could look at is you could look at what percent of the numbers less than your number go into your number. So we let, phi of n, this is the Euler torsion function. This is equal to the number of numbers m, 1 less than equal to m, less than equal to n. M is relatively prime to n. So this means m and n do not share a common factor. So what we could look at is we could look at, phi of n over n, or maybe n minus phi of n. This would be the number of numbers up to my number that share a factor. That's a little bit stronger than this. because 8 would share a factor. There's a lot of different things we could calculate. And this is one of the reasons why 60 is good. 60 splits up so many different ways. So here we would not want this, we want a more involved function, the divisor function. We want to count how many divisors does it have. And maybe look at numbers that have a really good ratio. Which numbers would have probably a bad ratio for numbers that, in fact, primes. So you probably do not want to work, base 11. Any L. Ron Hubbard fans? Okay, so the cyclos worked base 11 partly to just be pain in the asses to the rest of the universe. They weren't nice people. Yes?
Sorry, you just erased it, but what did you write next to Euler? It was like Euler or something.
Oh, the Euler torsion function?
Oh, okay.
Yeah, we're going to get into that in much greater detail later in the semester. This was just like a quick shout out to it. So the Babylonians worked base 60. Imagine you are in a Babylonian school now, and you need to learn your multiplication table. How many of you remember your multiplication tables? So how many of you have gone up to at least 10 by 10? I should see every hand up, or if not, just raise your hand and learn it tonight. Okay? How many of you know up your 11s tables? Really not that much you have to do, because all the way up to 11 times 9, 11 times 10 is not so bad. 11 times 11 is 121. 11 times 12, that's the only one you maybe need to learn. How many of you know your 12s table? 13 table. At this point we have a positional or place value system for numbers. If we can multiply 0 through 9, we can then get a number like 13 by breaking it up into 2 processes of multiply, add, combine. Imagine you're a Babylonian. What kind of tables do you have to, oh my God, you have to learn up to your 60s. And so how many multiplications do the Babylonians need to do? So we do things in tens, so we have to do 100. How many do the Babylonians have to do? 3,600. That is a lot to either memorize or to put on these hemiclade tablets that you carry around with you. But multiplication has some nice properties. What's a nice property multiplication has? It's commutative. So really it's not 100. Approximately what is it? It's not exactly 50 because we have the squares as well, but it's approximately 50 because multiplication is commutative. All right. Hey, it's a factor of 2 savings. We talked about that earlier. So if you're a little Babylonian, you just saved yourself 50%. Now, when you consider how much memorization, when you consider how many stone clay tablets you have to lug, this is pretty good. This is still more than you're going to really memorize if you're an ancient Babylonian. So the Babylonians came up with an interesting way to multiply numbers. If you've never seen this before, it may look like the stupidest formula you've ever seen in your life. But if you put it in context, it's brilliant, and it's the basis of a lot of our modern technology. So the Babylonians said x times y is x plus y squared minus x squared minus y squared divided by 2. So rather than doing one multiplication, we're going to do 3 squares, 2 subtractions, an addition, and a division. And this is actually progress. Why is this progress?
You can choose favorite of the numbers.
Well, no, I need to be able to do this for any x and y.
You only have to learn squares?
Only have to learn squares. Addition and subtraction are so easy, they're trivial. So all I need now is a table of squares. So that's 60, or maybe 120 if I have to go all the way up to twice 60. That's much better than 1800. This is, in so many ways, one of the greatest ideas I've seen in mathematics. What it's doing is it takes a really hard problem and reduces it to a lot of simpler problems. And most of the time in life, this is a good trade. I would rather do a lot of easy problems than one really painful problem. The other idea, which is lurking in the background here, is the idea of a lookup table. That if something is useful or important, you do it once and you save the result. And then it's available. Sometimes the lookup table is in your mind. Somewhere you've got 9 times 8 is 72. Any Sherlock Holmes fans? All right. So I think in the very first Sherlock Holmes story, Watson tells Holmes that the moon goes around the Earth. And Sherlock Holmes says, well, this has absolutely nothing to do with my life. I'm going to try to forget this as soon as possible. What? I believe my mind is an attic and I don't want to clutter it up with facts that are not important to me. You have to decide which information is so important that you want to store and keep it with you. Cell phones are much better than when I was a kid. My daughter was in for a very rude surprise the day she wanted a cell phone, and she asked my wife, well, Mommy, how old were you when you got your first cell phone? Really? And then my wife said, yeah, you could ask Dad when he got his, and it was much later than me. But cell phones, you have a limited computer inside. How does the computer do all the different operations it needs? It has a lot of lookup tables and a lot of interpolation functions. So a lot of these basic ideas are very important. I'm not going to cover it in class today, but in linear algebra, if you want to multiply matrices, you've seen that this is an order n cubed operation. You can actually do it in much shorter time, like n to the log of 2 base 7. And this is called the Strassen algorithm. I will post this. It is phenomenal how much savings you can get in these standard operations. If you spend the time, you can actually do better. And these things allow us to do computations that would otherwise be unapproachable. They expand the realm of what we can investigate. Okay, so we've talked about efficiency, we've talked about algorithms. Amazingly, we have ways now to tell if a number is prime without giving us a factor. And we'll do that later this semester. We will actually find ways to tell if a number is composite without actually being able to give a factor. Which seems strange, because the most common way to tell a number is composite is to say, here's a number that divides it. Okay. So, shifting gears a little bit. A huge part of this class is going to be experimental mathematics. I want you to try to figure out what patterns are and how to sniff them out. How many of you have not seen proofs by induction before? Okay, so everyone has seen proofs by induction before. There are 2 types of proofs by induction. Those where they give you the statement, and those where they don't. The ones where they give you the statement are significantly easier. You have an idea of how to attack things. If I want to tell you what's the sum of the cubes, if I sum the first n cubes, it's n squared n plus 1 squared over 4. It's much easier to prove this if you know that formula. If you don't, you can still prove it, but it's harder. So how do you find these formulas? Well, one of the things you do is you gather data. So what I want to do now is I want to do the cookie problem. If you've taken probability with me, or were in problem solving earlier today, you've already seen this. How many of you are considering a career in graduate school? Okay. Just to warn you what it's like, when I was a postdoc at Brown, the graduate students had a free food email list, where they would shoot emails to all the grad students and say, there's a talk at 4 o'clock in this building, followed by this type of food. And the guys would go, I can listen to that for pizza, or I'm just getting vegetables, no. And they would make these decisions. So I like to picture this with, I have P people, they're graduate students, and they're hungry. And I will assume that the people are distinct. If you are talking about engineering grad students, it's not necessarily true. But I will assume that this is a pure math graduate program where your professor does know your name. This is sadly not always the case. I actually had a friend in grad school, not in math, but the professor had their name wrong. And they were very shy and did not want to correct the professor, which led to real awkward situations when the professor was misintroducing them at conferences. I will assume that people are distinct, and if I get the cookies, it's different than if you get the cookies. Okay? I will assume we have C cookies, and they're all identical. And the question is, how many ways can we divide C cookies among P people? If you know the answer, it actually becomes very easy to prove this, and you can prove it in one line. if you know the answer. If you don't know the answer, it's much harder. So what I want you to do for Wednesday's class is I want you to choose a couple of values of C and P, gather some data, and see if you can sniff out a pattern. Have I talked about the online encyclopedia of integer sequences? Right. So there's a great website called the OEIS. And what you can do is you can insert a string of integers into it, and it will tell you all the sequences it knows that start like that, or have those numbers as a consecutive block, or have those numbers somewhere in it. If there are things known about the sequence, it will tell you. It's a wonderful website. Can someone tell me, let's say for definiteness, maybe P equals 5 and C equals 10. Can somebody give me a method to count, to find how many ways there are to divide the cookies among the people? I don't care if it's a good method. In fact, I prefer a really bad method. Yes?
Just go case by case.
Go case by case. So let's give the people names A, B, C, D, E. You could give them names, maybe Atlanta, Boston, Cleveland. Names that begin with the first letter of A, B, C, so that it's easy to glance down. This is very similar to our little f, big F. You want notation that's good. Okay. 10, 0, 0, 0, 0, 0, 10, 0, 0, 0, 0, 0, 10. I could easily fill up the rest of the class just going through all this. So the first question is there a faster way to do the brute force attack here? Can you write a computer program to do this? We'll spend Wednesday learning how to do some basic programming. It's a skill you really need to have when you leave. Can you do some simple cases and get a sense of what the formula might be? Okay, so does everyone understand the problem? Okay. So, this is a great example of being able to do things efficiently is going to be quite important. Problems like, well, I'll leave it like this for now. Okay, so now what I want to do is I want to review a little bit of calculus, talk a little bit about connections between calculus and primes, and motivate some of the things we're going to see later in the semester. Right now, this is still shopping period, right? I want to give you a little bit of a sense of where we're going to go in this course. What are we going to see? What kind of techniques? This is a first course in number theory, so I'm not assuming real analysis. I'm not assuming a lot of advanced machinery. So what this means is sometimes I will have to do a little bit of hand waving to say this can be justified. But I want you to get a sense of what the problems are, what the methods are, and why you might need a class like real analysis. Why you might want to do things rigorously. Okay. So, probably one of the most important numbers in all of mathematics is pi. Anybody know what pi is? Or approximations for pi? If you can't give me all infinitely many.
3.1415925.
Anybody able to go further?
3589793238462.
Unfortunately, you're not beyond what I can do, so I can't confirm. But I can at least confirm to how far you went, and I think you next few
Yeah, I always
digits.
learned to the edge of my calculator screen.
So that's an interesting thing as to why people know a certain amount, because that's how much was displayed. There's a lot of things like that. So, are there formulas to calculate pi? Well, yes. We have some formulas going back to geometry with perimeters and areas of regular n-gons inside a unit circle, and then looking at limits that can get us formulas for pi. So, one of my favorite equals in mathematics. This is going to be called the Gregory-Leibniz formula. Is the following. The integral from 0 to 1 of dx over 1 plus x squared. And this is a good way to just quickly review calculus. I know it may have been a while since some of you have seen calculus. Does anybody, and if you're in my probability class, you're not allowed to speak right now, anybody recognize the antiderivative of this function? Yes?
Is it arc?
It is arctangent. So, how many of you remember the chain rule from calculus? So, if you have f of g of x equals x, these are called inverse functions. All right, what's the derivative of x with respect to x? 1. The derivative of this side is f prime of g of x times g prime of x. So g prime of x is 1 over f prime of g of x. So if we know the derivative of f, we can actually get the derivative of the inverse function. So I want to find the derivative of arctangent because there has been a conjecture now that the derivative of arctangent is 1 over 1 plus x squared. Can anybody think of a good function to hit arctangent with so that I'll get x? Tangent. So the arctangent of x means the number whose tangent is x. So if I take the tangent of the number whose tangent is x, I get x. So using the formula, we get arctangent prime of x is 1 over tangent prime at arctangent of x. What's the derivative of tangent? So tangent is sine over cosine. So you get cosine squared plus sine squared over cosine squared. So you get 1 over cosine squared. So the derivative of tangent is 1 over cosine squared, which then becomes, since I'm taking reciprocal here, becomes cosine squared. So this is cosine squared of arctangent of x. As an aside, I absolutely hate the fact that 1 over cosine is associated with secant and 1 over sine is associated with cosecant. This is an example of bad notation that we are stuck with. Now, unfortunately, what the hell is the cosine squared of arctangent of x? I've written this down, but this isn't that meaningful to me. So this is going back to our theme of trying to write things in a way that makes sense. Well, let's think. I want an angle whose tangent is x. Tangent is opposite over adjacent. Let's make this x and let's make this 1. The tangent of this angle now is x. What would the hypotenuse be? X squared plus 1. Or 1 plus x squared either way. And then take the square root. So now, if I want to take the cosine of arctangent of x, the cosine would be 1 over square root of x squared plus 1. And so now I will get cosine squared is 1 over 1 plus x squared. So this is just a nice way to review calculus. To see the power of the chain rule, to see the power of inverse functions, to see the advantages of good notation. So this integral we can actually relate to arctangent. Nice. All right, so we now know that the integral is going to be arctangent at 1 minus arctangent of 0. What angle has a tangent of 0?
0.
And what angle has a tangent of 1? What is it? Pi over 2 or pi over 4? Pi over 4. So the integral from 0 to 1 of dx over 1 plus x squared is going to be arctangent of 1 minus arctangent of 0, which is pi over 4. Okay. Have you ever seen anything that looks like 1 over 1 plus x squared? If you've been in probability, you're not allowed to answer. Have you seen anything that looks like 1 over 1 plus or minus something? Does that ring a bell from anything you've seen? Any formulas? Have you ever seen anything that's... Whoa, okay, now I see your head shaking. What is this? One of the most famous formulas in math. This is the geometric series, 1 plus r squared plus r cubed, if the absolute value of r is less than 1. How many of you have seen this? Right. This is the geometric series formula. Okay? A simple proof is if we let s be 1 plus r squared. If we look at r times s, it would be r plus r squared plus dot dot dot. If we subtract, we get 1 minus r times s equals 1. You can do things a little bit more rigorously and show that everything converges. You can do a finite geometric sum and then take the limit. But then when you divide, you get s equals 1 over 1 minus r. And as long as r is less than 1, this makes sense. I'm just trying to give a quick explanation here. So I should write this as 1 over 1 minus negative x squared. And this is the real reason why I want to do this problem so early in the semester, is I want to give you a sense of what I want to cover in this course. It's not necessarily the material, it's the thought process. Because if I now write this as 1 over 1 minus negative x squared, this looks like a geometric series. And I could write this as 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus dot 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 dot. So this would be 1 minus x squared plus x to the 4th minus x to the 6th plus dot 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 dot. Okay? And now, we've got just enough time. Let's integrate 1 over 1 plus x squared from 0 to 1. I have the integral of 1 dx minus the integral from 0 to 1 of x squared dx plus the integral from 0 to 1 of x to the 4th dx minus the integral from 0 to 1 of x to the 6th dx. What illegal thing may I have done?
You can't always take an integral of a sum.
Right, you can't always switch orders. You know, the integral of a sum is not necessarily the sum of the integrals. It is if it's finite. So you might remember things like Fubini's theorem from Calc 3. When can you switch orders? You have to be very careful. It turns out you can switch orders here. This can be justified. So this is just pi over 4. All right, what's the integral of 1 from 0 to 1? 1. The next is I integrate x squared. I get x cubed over 3 from 0 to 1. What do I get? 1/3. What's the next one? 1/5. What's the next one?
1/7.
1/7. Here is a formula for pi over 4. I'll leave it as an exercise to deduce a formula for pi from this. It's not that bad. This is actually a crappy formula for pi. The reason it's crappy is you talk about how quickly does it converge. It converges slowly. You can even estimate. What's nice is the terms are alternating and they're decreasing in magnitude. So if I stop here, have I over or underestimated pi? I've overestimated. And the amount I've overestimated by is at most 1/7. If I stop here, I've underestimated pi by at most 1/9. So this formula, it's going to be roughly, if I go up to, the nth odd number, it's going to be on the order of 1 over n. So if I want 10 digits, oh dear. To get 10 digits of pi, I've got to use a lot. In principle, this gives me a formula to calculate pi. In practice, this is a very slow, painful formula to use. And so, this is very much related to our quest for trying to do these things quickly, efficiently. There are better formulas for pi. There's something called the Riemann zeta function and generalizations called L functions. This turns out to be the special value of an L function. There's a better value of the Riemann zeta function, which gives a better formula for pi, actually for pi squared. All right. So in terms of what I want to cover today, I think this is basically as far as I want to go. The only thing that we don't really have time to do is to show how a formula like this for either pi or pi squared implies that there are infinitely many primes. Now that is a strange result. Why should a formula like this have something to do with the irrational, with the infinitude of primes? So that's something we will hit upon later in the semester. So again, you're going to have a mix of theory and experiment. I really want you to gather data and figure out how to process it and conjecture. It's much easier when someone gives you the answer, but post-Williams, you're going to be in the situation where you're going to be trying to figure out what's going on. And that's why that's a very valuable skill. So the pace of this class is going to be, I think, a little slower than maybe some of the other 300 classes you've taken, especially if you've done probability with me. I really want to spend time on the thought processes. And I want everybody to be understanding this and clear with this, that you're not going to be upset if we're not traveling at warp speed. All right, so this is a good place to stop for today.